Thanks for joining. This is a SolidWorks Plastics town hall. We're happy to have you guys here. It looks like we have a really large audience. The topic here is going to be how to predict and avoid some common injection molding defects. And we're going to have some presenters and we're going to have some questions. So my name, well, first of all, our three presenters today and the most important people are Dr. Robert Malloy, who's a Chairman Emeritus at UMASS Lowell in their plastics engineering department, and he's also the author of a book that deals with plastic injection molding defaults. So he'll be talking about some common injection molding issues, and we'll be following that up with some presentations that will be done by Ramesh Lakshmipathy. For those of you that don't know Ramesh, I don't know if you guys have done other town halls before. Ramesh is a leader in this SolidWorks simulation space. He manages the technical team, the SolidWorks simulation technical team. He's been at SolidWorks for nearly 20 years, has worn various hats at SolidWorks, including being a product manager for our motion tool. He was in technical support, doing worldwide technical support and training for a while. And now, again, he manages the SolidWorks simulation team. And, oops, finally, sorry about that, guys. We have Peter Rosinski, who, sorry, Peter, I don't have a slide for you, but Peter is our product manager for the SolidWorks Plastics product, and Peter is going to be talking about what's new coming in SolidWorks simulation plastics, or SolidWorks Plastics in the upcoming years. As with respect to the agenda, this is kind of what it's going to look like. Dr. Malloy is going to be doing a discussion of some of the common issues associated with plastic injection molding. Then Ramesh is going to be doing a demo of plastics, or how SolidWorks Plastics kind of can address some of those issues. We're going to go back to Dr. Malloy for some more advanced topics associated with injection molding, and then Ramesh is going to show some more advanced capabilities available in SolidWorks simulation plastics. And then we'll finish it off with Peter Rosinski kind of giving an overview of what's coming new, or what the kind of the new features that are going to come in SolidWorks Plastics in the upcoming releases. And then there'll be plenty of time for some Q&A. And we have multiple panelists that will be able to answer questions. My name's Omar Zoni. I'm kind of just the MC here, kind of making sure everything goes okay. I'm also a simulation guy, so I might be answering some questions also, but kind of not important to this thing. The most important people are going to be Dr. Malloy, Ramesh, and Peter Rosinski. So that being said, just a little bit of logistics about how this works, just so you guys get an understanding. So, you know, there are a handful of us here that are kind of doing the virtual town hall. We've got over 200 or 300 people in attendance, so there are a lot of you guys. You guys are going to be muted. Hopefully I'm coming through clearly with the audio and visual. In order to ask questions, you just need to go use the GoToWebinar GUI, and there'll be a questions section. Just go ahead and ask your question there, and then towards the end of the broadcast here, we'll go ahead and answer as many questions as we can. Any questions that we don't get answered, we're going to keep a log of those questions, and we will reach out to you individually. So we'll do our best to answer as many questions as possible. Again, there are over 250 people in attendance, so we might not get to all of them, depending on how inquisitive you guys are, and we would love as many questions as possible. That's the point of this. That being said, one more thing, just so you guys get a feel for, you know, where the people in attendance are. These are some of the hot spots, so we used an application available from Google to kind of show where the people in attendance are for this thing. You guys can see a lot in California, up in the Pacific Northwest, and the Northeast. We just did North America. There are also people joining us from around the world, but obviously this, you know, based on the timing of this, most of the people are from North America. Wow, sorry, Peter, there's your introductory slide. So that being said, I'm going to turn it over to Dr. Malloy now, and Dr. Malloy, go ahead and you can get started with your presentation, and we'll go from there.
All right, so as Omar said, I'll start things off, and then Ramesh will kind of demonstrate some of the concept I've talked about, doing some simulations, and then I'll come back and finish up with some other topics. The focus really today is most heavily weighted toward the subject of knit lines or weld lines. which is a very common problem in injection molding. Basically, anytime you have a flow front that splits and recombines during the mold filling process, you end up with this defect, generally called a knit line or a weld line. Personally, I use those words interchangeably. There's a lot of terminology issues that could be subtly different here, but generally speaking, I would consider the terms weld line and knit line to be equivalent, and I use both terms. Probably I'll use both terms today, just not consciously, but sort of unconsciously. The term line here is really an oversimplification or almost a misnomer. What we see when we see a knit line is actually a line on the surface of the molding, but it's more complicated than certainly the line. It's really a plane. The line has a certain distance and the part has a certain thickness. And if you multiply the thickness of the part times the distance of the line, you really have an area that is a plane, or what I generally like to call the weld zone. The line itself is part of the issue. It's visible. But what's happening internal to the material is equally important, and we need to think about that. Generally, the knit line is considered a defect. Sometimes it's a sort of very severe defect, and sometimes it's a very minor defect. But typically, you're concerned with three things. One would be structural integrity. The knit region is generally a region of reduced mechanical performance. So in parts where you have sort of structural requirements, this is a pretty significant concern. It's also a cosmetic defect or a blemish. Generally speaking, the weld line itself that's visible on the surface is a cosmetic defect, sometimes visible just by the naked eye, and sometimes it's there, but it's less obvious. Unfortunately, these things can be very difficult to predict at the design stage, but that's sort of the point of this presentation, is we really like to get a handle on as many of these problems as possible right from the get-go. And oftentimes, I find one area that people overlook is the chemical resistance in the area of the weld. So many plastic parts are subject to some sort of chemical in the application, and typically chemicals will attack plastic parts in areas where the part is under stress, such as at the gate on the molding itself, or in the case of weld lines or knit lines, they generally exhibit reduced chemical resistance as well. So we're concerned about this phenomenon for those three reasons. Okay, and we'd kind of like to take this as a sort of holistic approach here and think about all the factors involved. Certainly the design of the part is probably the most significant thing in determining the locations of the knit lines. But we're also concerned about how does the material itself affect the knit line. Knit lines are a problem with some materials more than other materials. So the material is certainly a factor. And while it's beyond the control of the designer, processing issues have a tremendous impact on knit line quality as well. So changes in variables associated with molding, such as melt temperature, injection speed, et cetera, can have a huge effect, as does the design of the tool. So the combination of the part design, the tool design, we really need to think about that. The integrity of the weld, to a large extent, or to sort of the most significant factor involved, is the molecular diffusion that happens after these melt fronts meet. So in other words, we really need to have molecules from one melt front crossing over into the other if we're going to achieve the strength, the chemical resistance that you'd like to have as it would be on the rest of the part. Predicting the location of the weld line is always a concern to the designer, and that's generally relatively easy, either with just engineering judgment if it's a symmetrical part, or with simulation if it's a more complicated geometry. So simulation software is invaluable in helping indicate where the locations of the knit lines would be. But we're obviously also interested in what the knit line will look like, the structural integrity, and the chemical resistance. But this is by far more challenging than location, based on you know, the simulation and predicting what's going to happen. So the prediction is not explicit in terms of things like mechanical performance, but you can certainly use the simulation results to gain a tremendous amount of insight into what's going to happen. Thinking about what happens when these melt fronts meet. The flow inside the injection mold is generally considered, you know, sort of in a fluid flow, non-isothermal fluid flow, unsteady state, laminar flow. It's obviously a very complicated situation because the melt is significantly hotter than the mold. But we're developing a frozen layer, and we have laminar flow through most of the cavity, with the exception of the melt front itself. And this is the area that's of most interest to us when it comes to knit lines, because these melt fronts are going to come together, and when they do, the flow is not laminar, it's really a fountain flow. It'd be like taking a hose, shooting it straight up in the air, and at the top it would split. And that fountain flow effect can have a huge impact on what's happening in the weld zone. We're also very concerned with the gases that are in the mold, air, possibly moisture, possibly volatiles from the melt front, and we need to make sure that those gases are vented. And if they're not vented correctly, then the melt fronts will not join together correctly. So venting is a huge issue when it comes to knit lines, and it's really a mold design issue more than anything else, but it's something that we sort of really need to get a handle on. We can also have discoloration in the weld, largely because the melt fronts are in contact with oxygen, and that may be part of the appearance issue. Any gases that are trapped, even if they don't prevent the melt fronts from joining together properly, are likely to create a small V-notch at the surface against the core and against the cavity. So the line itself is not just sort of a visual line, it's actually a small depression, depending on how the mold is filled and how effective the venting is. So that's something we're going to have to think about. We're also now thinking immediately when the melt fronts meet, what is the situation? The key here again is to make sure the gases are vented and that the melt itself has enough mobility or a lower viscosity that will allow melt or say polymer chains to cross over the interface and interact with one another. Because without that sort of bridging the gap with the chains, then the strength, the chemical resistance, and so on will be greatly diminished. So any variable in terms of thinking about knit lines or weld lines, any variable that's going to promote low viscosity is probably going to be beneficial. So that means that using materials with, say, a lower viscosity or a higher melt flow rate would be advantageous for parts that contain many knit lines. While we generally like to use higher molecular weight plastics because the properties tend to be better, if the part has many knit lines, then you may want to rethink that, because the knit quality is probably the sort of weak link in the whole system. We'll talk about the processing variables later, but again, any variable that promotes sort of hotter melt fronts is going to be beneficial. We're also concerned that if possible, we would like to have the knit lines flow after the melt fronts meet. So there are many reasons that these flow fronts can divide and rejoin, but if we can rejoin them in such a way that they will continue to flow after they meet, that's generally positive. So there are several reasons why the flow fronts divide. The first is having through cores within the mold cavity itself. So anytime we have to have material flow around an object, typically an insert of some type that would be considered a through core, meaning all the way through the thickness, or even a blind core in some cases will produce weld lines. We're concerned what's happening at the meeting points. Here we'll make a sort of further classification in terms of terminology. In the top left-hand figure, the material flows around a core and then meets on the back side and stops. So there is no downstream flow component, and this kind of weld would be typically called a butt weld. Sometimes people use the term cold weld, but effectively what the characteristic is that there is no downstream flow component. A meld line or a streaming weld, which you would see in the bottom left-hand corner, is a knit line where the flow fronts meet and then flow continues in the downstream direction. And this typically is less severe in terms of visual appearance, strength, chemical resistance than the butt weld. The part on the, or just with a meld line as it's called, the line oftentimes can disappear. So on the figure on the lower right, sort of I'm showing material has flowed around a core, creating the knit line, but the knit line is only visible for a certain distance from the core toward the end of flow. And the black part above that figure shows that exact situation where the part is gated. There's a round insert pin inserted into the mold, and material flows around that round pin and joins on the back side. And you can see that the knit line only extends about 50% of the way to the end of flow. And that's oftentimes the case. But here we have almost exactly the same situation where we have a gate on the left-hand side of the part, a core, round hole, and a knit line on the back side of the hole. It may be a little bit light in the image, but that line extends for the entire distance of the molding itself. So sometimes the knit line disappears and sometimes it doesn't disappear. So there's no, it's one of the frustrating things with knit lines is there's no easy way to know ahead of time whether this will happen or will not happen, because it varies depending upon the material you're using, the pigment system, and a variety of other factors. Another important thing to think about with knit lines is the relationship between gating and knit lines. So the geometry of the part itself will determine the location of the knit lines in conjunction with the gating scheme that's used. So I use the term gating scheme, which essentially is the number of gates, the locations of the gates, and the types of gates. So in the left-hand image, a gate system, say located on the left-hand side of that part, would produce a series of knit lines after flow around those white cores. Those are through cores, producing holes in the part. And you'd have knit lines, specifically butt weld lines, really, behind each core. And it would be very difficult to vent the gas from those locations. You would have to basically have each core be a separate insert so that you could vent between the retainer and the insert, and so you can allow for the air and gases to escape, which is fine, but over time those vents have a tendency to get clogged and the mold would need more maintenance, and they're not as effective as edge vents. So whenever possible, we'd like to gate the part in such a way that the knit lines form along the parting line. So in the case in the middle, the material would be injected through the runner, through the gate, flow up vertically, and produce the knit lines on the back side of the cores, which in this case are easily vented because we can use parting line vents. The advantage, again, is that they're more efficient, easier to maintain, because every time the mold opens, you have access to the vents and they could be cleaned. The quality of the knit lines would be better when you can have edge vents as opposed to internal vents. The second reason we're getting knit lines is multiple gates. So anytime we have more than one gate on an injection molded part, we're going to introduce knit lines, even though the part itself does not have any through cores. So the part on the left could be molded with one gate, and if it was, it would not have a knit line. In this case, the designer decided to use two gates, which introduced a knit line right down the center of the part because it's very symmetrical, and we're pretty confident that's where the knit line would be, and in fact it was. But for whatever reason, the designer of this part felt two gates would be better than one gate, even though you're adding a knit line. The gear on the right is the same. The gear has three gates. Therefore, there are three knit lines, each 120 degrees apart. Again, the simulation will give us more information on the quality of the knit line, but certainly in this case, because of symmetry, we know the location of the knit line. But we need to balance the addition of more gates versus the creation of knit lines. So the gear is a good example. The gear could be molded with one gate. It could be molded with two gates. It could be molded with 8 gates. But in this case, the gate would be from, say, a 3-plate mold or a hot runner mold onto the face of the gear. And if you use one gate, you could fill the mold. It's a small part. There's no problem with pressure drop. The issue would be really one of area shrinkage, in that you would get less shrinkage near the gate than away from the gate, and the gear itself would be out of round. And so it would be more like an egg shape. So by adding more gates, you make sure that more material is closer to the gate and that the pressure history, regardless of where you are in the cavity, would be very similar. So we're producing a rounder gear. It's still not perfectly round, but in this case, it would be acceptable for most applications. And the negative side effect of adding more gates would be the addition of 2 more weld lines. On the other hand, because we now have more gates, we can fill the mold at a faster injection rate. So the time required to fill the mold would be reduced. So yes, we have more knit lines, but the quality of each of those knit lines would be better than a single knit line. So it's always a balance of, introducing more knit lines by introducing more gates, which again has its benefits, but then we have this disadvantage associated with the knit line. And the third reason that we're getting knit lines would be one where we don't have symmetrical parts and we have a more complicated flow situation, oftentimes due to the fact that the part may have variable wall thickness. So in this case, the simple disc, which has a rim around the outside that's thicker than the central region of the part. So the material would have a tendency to flow at a greater rate around the thicker section and meet up upon the backside, and possibly even have an air trap in a location of the part where you would have difficulty venting. So in situations like this, you really want to design this issue out of the part if at all possible. And Ramesh will go through an example that demonstrates this. But by adjusting the wall thicknesses and the filling conditions, you're hopefully able to eliminate knit lines from situations like this. But this is a classic situation generally called race tracking. And again, the simulation will point out the locations where these occurrences could happen and allow a designer to adjust the wall thicknesses of the part or the gating scheme again in order to prevent this from happening. So at this point, I think I'll turn it over to Ramesh, who will do some simulation and make an attempt to answer these questions that a designer would have. In picking a gating scheme, will I have knit lines? And if so, where will they be? And is there any information that can help me determine if this is likely to be a structural or a cosmetic problem? So Ramesh, I think if you want to start now, I'll...
Hey guys, Ramesh, before we get over to your demo, we're going to do a quick poll. So let me just share my screen here real quickly. We're going to do our first poll question, guys, if you guys can just answer it.
All right, so there's a lot of really valuable concepts that Dr. Malloy discussed. So I'm going to illustrate some examples using injection molding simulation software, how you can actually be able to predict some of those defects and address them early on in your design process. So the first example we're going to look at is a keyboard cover. Typically you see this on your laptops, but the point that we're trying to highlight in this example is single gate versus multiple gates, or two gating in this scenario. So you can very well see from both these images, on the left side we have a single gate on one end, and then we also are saying, okay, let's try a double gating scenario to see what happens. So in SolidWorks Plastics, which is an injection molding software, you can quickly go ahead and set the problem up. But the key to understanding and making good design decisions is really getting into the visual aspects of things, so really getting a window inside your mold. So as illustrated here in this video, as you can see the difference in between a single gate and two gates, where it's showing how the flow front is actually flowing from right from the runner system through the mold cavity. Now, in terms of weld line, which is the bulk of today's discussion, when you have a single gate versus a two gate option, the single gate actually creates lesser welds, as you can see, weld lines, as you can see highlighted with these round red arrows, circles. And what this means is, well, the whole idea is if you use a single gate, you can probably have more injection pressure requirements, less weld lines. That's a bonus. But when you have two gates, as shown here on the right side, you can see that it ends up creating more weld lines. But as Dr. Malloy alluded before, the key to understanding, even if you might be getting more weld lines, the key is to understand if those weld lines are, really strong enough. The integrity of the weld is what you can predict, in both these scenarios using plastics injection molding software. So how do we go about doing that? Well, we can investigate, we can probe along the thickness of the cross-section where the weld line actually forms. And this picture is illustrating, for example, with a single gate scenario, what the temperature distribution looks like on that cross-section where the weld line is actually forming. So to summarize, what happens here is, if you look at the range of the temperatures, so it averages about 280 degrees Celsius around the weld line. And when we actually also probe in terms of what's the melt temperature at the gate, so keeping a note of that, so that's about 290 degrees Celsius. So that's giving us a temperature differential of about 10 degrees Celsius. So that, like Dr. Malloy alluded earlier, that the key here is to keep the melt front, or the melt temperature, as high as possible, closer to the melt temperature at the gate. So here you can see that with the single gating option, even though you get less welds, the integrity of the welds might be under question. Now, the same scenario with two gating option, same probing of cross-section of the part where the weld line actually forms. If we compare the temperatures, that averages about 286 degrees Celsius, which is really close to the melt temperature at the gate. So that's giving us a delta temperature of about 4 degrees Celsius, which is really, what we want. So there is advantage of, in terms of gating, you can have multiple gates. It can produce more weld lines, but the integrity of the weld lines can actually be much better compared to a single gating option. So in conclusion, the integrity of the weld line formation improves with, multiple gating scenarios. It also affects the the delta temperature. So in this case, we compare the temperatures of the melt front at the gate as well as where the weld line actually forms. And so we can expect the weld lines to form at a temperature closer to starting melt temperature in a multiple gating scenario. The next example illustrates the race tracking effect that Dr. Malloy talked about earlier. So here's a simple cap example, but the image on the left side is illustrating a non-uniform wall thickness. You can see that we have a thin section on the top versus a thick section around the sides. Now, traditionally, you would want, gate this type of a design from the top, right? But again, you might, that's going to lead us to gating from thin to thick section, which contradicts, how we want to gate, otherwise, right, from thick to thin. So we're going to look at, how the flow front actually behaves or flows in this non-uniform section versus on the right side, we're going to just make a simple design change and make the wall thickness uniform everywhere. So this is illustrating how that the flow front animation looks like, or how the flow flows from the gate all the way to the end of the part. And you can clearly see on the animation on the left side, you can see that race tracking effect just because of you have the non-uniform walls, thin on the top and thick on the sides. And you can see that the more uniform option or the design is having a more, it doesn't actually show that race tracking effect. What's interesting is when we take a little bit deep dive into understanding where the weld lines and air traps are. So on the non-uniform section, you can see that we have the weld lines clearly form, and it's very dramatically forming across towards the end of the fill. But also you can see the air traps that form. One is actually right on the top, which is probably not desirable just because you might have to do some specialized tooling to vent out that air trap. But the air trap at the bottom is right on the parting line. So that's good. That's okay. But we are looking at ways to actually not only get rid of the weld line, but also at the same time eliminate those air traps. So a uniform thickness design, as shown in the picture here on the right side, you can see that the same workflow, same process parameters, just making that change in the design, making it more uniform thickness, literally eliminates the weld lines and also eliminates the air trap on the top. So bottom line is race tracking can occur due to varying wall thickness as well as where you might actually gate the cavity. And the race tracking filling variations can lead to unacceptable air traps and weld lines. So injection molding simulation software can actually be used, as I showed you, to try out multiple water scenarios. And it's a great way to understand and predict and identify errors, maybe common manufacturability issues upfront in the design process before you cut metal. So I'm going to hand it back to Dr. Malloy, and he's going to continue with the rest of his presentation.
Hey guys, real quickly before we go back to Dr. Malloy, and thanks Ramesh, that was a great demo. I just wanted to make sure to ask you guys, please submit questions. We're getting some questions now. We'll be periodically answering them during the presentations and Ramesh's demos, but for the ones that we feel are really relevant, we'll be sure to answer them in the audio portion of the Q&A at the end. And one more thing before we go back to Dr. Malloy, there's also a handout available if you guys are interested. So underneath where you guys would ask questions, there's a handout that you guys can download that is a really interesting white paper from UMASS Lowell. So we'll hand it back to Dr. Malloy now. He's going to cover some more advanced topics associated with plastic injection molding. Then we'll hand it back to Ramesh to show how SolidWorks plastics can handle those, and then we'll move on to Peter Rosinski's section. So keep asking questions, and again, thank you guys for being engaged.
Okay, thank you, Omar. And Ramesh, that was great. That really demonstrated a couple of the points that I think are important. One of which is it's really important for designers to be involved in the decisions related to gating on injection molded parts, because it oftentimes does require part design change, wall thickness variation, etc., that only the designer can do, make these decisions. So I would encourage everyone to please be involved in that aspect. I wanted to touch upon materials here a little bit because weld issues are very, very significant for some materials, and they're almost insignificant for other materials, and there are reasons for that. When I think about plastics, I always think about 4 variables. When you're saying what makes one plastic different from another, well, it's one of these 4 things. The first of which is very important here is molecular weight. As we said, we generally like to use higher molecular weight materials, in other words, low melt flow rate materials, because they tend to have better properties. But because they're more viscous, they don't do so well when it comes to weld line situations. So if you have a part where you have lots of cores, I think it's beneficial to consider using higher melt flow rate grades of material because you'll have fewer problems and you kind of know what you're going to get, and there are fewer surprises. The structure of a plastic is also very important. It's much more difficult to think about, but there's no question that the link structure or the repeat unit has a significant effect on the ability of the material to weld back together again. Maybe it's a topic for another day, but for example, materials with low TG tend to weld together better than materials with high TGs. Additives are another big factor. All plastics contain additives. All. Maybe very low concentration and maybe insignificant, but sometimes the additives are used at percentages as high as 30, 40, 50%. So they could be powders, they could be liquids, they could be fibers. We'll specifically look at fiber reinforced materials because they're known to have serious weld issues. And fiber reinforced plastics are used in structural applications, oftentimes metal replacement applications where you need stiffness and strength. So definitely they sort of have to go under the microscope here. And then there's, of course, the morphology. Most plastics are either semi-crystalline or amorphous, probably 50-50 roughly in terms of thermoplastics. A little more difficult to think about. I'm not sure you can make a generalization that would say that knit lines are more of an issue for one type versus the other. It really depends on more factors than just the morphology, but certainly morphology is a factor. One point I want to make straight up front here is to say that much of this is unknown because generally speaking, material suppliers do not publish weld strength data. So if you look at a data sheet for plastic or a database, you'll find mechanical property data. Could be tensile stress at yield, tensile stress at break, break stress, break strain, modulus, things of that nature. Weld strength, probably not there. It can be generated, and if it is generated, it's generated using a test sample that's gated with 2 gates as opposed to the normal test sample, which has 1 gate. So the sample on the right would produce a test bar and a tensile bar with a knit line in the center as a result of the gating scheme that was used. And it would be helpful if the material supplier could generate this data and provide this data, but in fairness to the material supplier, the weld strength is affected by so many variables, including all of the process conditions, that they'd have to generate sort of lots of numbers to cover the range. So it's sometimes available, generally not available, more often than not. And there really are no rules of thumb that say, the weld zone is 30% weaker than the zone without a weld. And there just are no rules of thumb like that, at least in my opinion. So you really need the actual data itself. And here's an example of some material supplier weld strength data that was generated on a series of different plastics, most of which are glass fiber reinforced grades. So if we look, for example, at the polypropylene materials, the top 3 materials in the table, we see that as the glass fiber concentration increases, goes from 0% up to 30%, then the weld strength retention factor, which is the strength at the weld relative to the material strength not at the weld, multiplied times 100, varies from 85% with no reinforcement down to like 34% with 30% glass reinforcement. So yes, glass reinforced materials are great. They provide strength, they provide stiffness, but the weld zone is going to be significantly different than other sections of the molding. So you want to be really careful to make sure that that weld zone is not in an area where structural integrity is important, right, where stresses are high. This happens largely because of this phenomenon that we saw in the beginning where we have fountain flow at the melt fronts. So yes, we have laminar flow for the bulk of the part, but when the melt fronts meet, they come together as two fountains. And that creates an orientation which is completely different in terms of direction than it is in other sections of the molding. In addition, you're not having glass fibers cross over through the interface, and therefore you're not achieving the same level of strength. So while I would say that weld strength numbers are hard to come by, if you are going to find them, you probably are more likely to find them for certain grades of material, specifically glass reinforced materials, because it is such an issue. Other factors or other additives are also important. So for example, pigments. There are two parts shown here. Both have two gates, and in one case the weld line is very visible, and in one case the weld line is not very visible. And effectively it's the same base polymer, but the pigment system is different. So the part on the left is molded or compounded with a pearlescent pigment. And a pearlescent pigment is really a flake. So it's a platelet that has some sort of coating on it to give it the color effect. People really like these kind of pigments because they're almost metallic looking. They give you an interesting look, but at the weld zone, because the orientation of the platelet is different, the appearance is very, very different. And so it's just something that's hard to predict up front, but just be aware that certain pigment systems can create very visible basically weld lines in this case, because again, we're not seeing through the thickness of the part. The part on the right is really compounded with we'll call it a polyhedral pigment, which effectively has a length, width, and thickness that are all very, very similar. So therefore, the orientation of the pigment is not a factor. Another issue relates to, let's say, insert molding. So the part on the top right is a compressed air fitting. It has an HDPE overmold to really give it sort of a more ergonomic feel. It's gated on the back side, directly the opposite of where the crack is, and that crack is a catastrophic failure. So the crack is occurring at the weld line. Now, the crack is not occurring because the part was subjected to a mechanical stress or a chemical. The crack is related to the fact that the material wants to shrink about 2 or 3%, because HDPE is a semi-crystalline plastic, shrinks roughly, let's say 2.5% or 0.025 inches per inch or meters per meter. And when we think about weld strength, maybe we shouldn't think about strength. What we should really think about is strain. Welds can be strong. They could be 90% as strong as the material would be otherwise. But what a weld will not do generally is stretch a long distance before it breaks. So in this particular case, if we look at the stress strain curve, the strength of the weld is pretty good, but the breaking strain is very low. And in this case, if the breaking strain is less than the mold shrinkage value, then the weld line will crack due to the fact that the steel will not let it shrink, and it's effectively putting the weld in a state of tensile stress. And it indeed did fail. So what could you do to prevent this? Maybe use a lower shrinkage material or material that would have a greater breaking strain. The part, it does have a very small gate, which would mean that it's difficult to pack out, and probably with a bigger gate, you probably could reduce the mold shrinkage. And there's all sorts of things you would do in processing to keep that weld zone hot. When those melt fronts meet, temperature is the key. Again, mobility of the molecules, fast fill, high melt temperatures, and in this case, preheating the metal insert would probably help a lot as well, because you're you're really losing a lot of heat to the insert itself, because the insert is made from a conductive metal. So that's a sort of a whole different situation, but also very common. So what really ultimately we're trying to do here is to figure out what can we do to minimize this issue with welds, whether it be, again, the structural, the visual, or the chemical resistance. So the very first and most obvious thing is to really try to put the welds in locations where they're the least harmful, right? So in terms of cosmetics, in terms of stresses, this is where mold filling simulations are invaluable, right? It is the gating scheme, the combination of the gating scheme and the geometry of the part that will determine the locations of the knit lines. Ideally, again, try to use materials at a higher melt flow rate, where you're going to have fewer problems with knit lines. Even though, again, on paper, higher molecular weight materials always look better. But if the part has many welds, then knit lines, then maybe that isn't really the way it's going to be in real life once you actually make the mold the parts. You're trying to disguise the knit as much as possible. I'll show an example with surface texture, but you could have labels. In extreme cases, plastic parts get painted. You really try to avoid painting plastic parts as much as possible. That's one of the advantages, is we have color throughout if we use pigments. But if the weld is that critical, then painting is sometimes really the only solution. Keeping things hot, again, as a process variable, we said mold venting, I can't stress enough, is critical. Not just at the weld zone. Mold venting is extremely important just in terms of being able to fill the mold faster. The more venting you have, the faster you can fill. And especially you need venting in the areas where the welds are to cut down on the size of the V-notch, avoid possible gas traps, and so on. Again, keeping the welds along the parting line, as Ramesh showed, is the best location, because that's the easiest place to vent. In extreme cases, you can use overflow welds, which I'll show an example. And I think Ramesh will touch on another example where we're using valve gates that are sequenced in order to eliminate knit lines. So this is generally most common for larger parts, such as automotive bumpers or a large TV panel. But if you can use valve gates, they offer a lot of advantages for many other reasons as well, but they certainly can be very helpful when it comes to knit lines. So in terms of process variables, my point here is that if we look at a typical injection molding pressure time curve, what's most important when we're thinking about knit lines is what happens at the beginning of that curve. Because once we're 1 second, 2 seconds, 3 seconds into the molding cycle, it's already done. The knit is either good or it's not good. What happens 10 seconds into the cycle is not important, right? What's important is how fast can I get the material in the tool? What's the melt temperature? If I use more back pressure, that would increase melt temperature. If I use a higher barrel temperature, that would increase barrel temperature. Fast fill is sort of the best approach, in my opinion, simply because it doesn't lead to an increase in cycle time, but gets that melt into the mold as quickly as possible, as hot as possible. One downside of that is that fast fills complicate the venting process to some degree, and you sometimes like to slow the fill down towards the end to assist with venting. But again, more venting is critical in parts with a lot of weld lines so that you can fill fast. I also put reduced clamp force, because if you don't need a lot of clamp force for the part that you're molding, if you have extra clamp force, then you can back off And that also helps with venting because you're sort of not keeping the air as tightly held within the cavity. But pack pressure, fill speed, melt temperature, these are all critical variables for knit lines. The surface finish, as we said, has a huge effect. So this is similar to the figure I showed earlier. What we really have here on the right is a disc which is sprue gated, meaning that the gate is in the center of the part, and it has a series of inserts that are, this part is roughly about 5 inches in diameter. Each of those inserts is right around an inch in diameter. And then there's about a 1/4 inch through hole in each of the areas where the insert is located. So the weld will form on the back side of the through hole, and by looking at the surface of the part, I just picked 2 examples here, A and B. One is a very glossy surface. It's a surface designation is an SPI A3, or now called plastics A3, which is a pretty highly polished surface. And we see that the knit line is very visible. It's a meld line. It's a partial meld line, but it's certainly very visible to the naked eye. And if we look at the same part, same material, literally the same shot, and we look at the textured surface, you don't see the knit line. It's there, but it's less visible. So probably the most significant way to disguise a knit that is going to be there would be with textured surface. Certainly you can tweak again the mechanical performance, the chemical resistance with process variables, but this is a very clear example that shows surface finish is pretty critical. So generally rougher surfaces are better in terms of disguising the appearance. And then I had mentioned the overflow well. This is sort of an extreme example, be for more limited production situations, but imagine something like a tennis racket. As Ramesh had said, you need to gate from thick to thin. So a tennis racket would typically be gated into the handle area because the handle area would be the thicker location, and the end of flow would be down at the top portion of the racket, and you'd have a pretty severe butt weld line. By adding an overflow well, what you're doing is changing the butt weld line into a meld line by introducing a downstream flow component. And as we said, anytime you can have downstream flow, it's better than not having downstream flow. The disadvantage here is that overflow well, depending on the application, would most likely need to be removed as a secondary operation after molding. So it's just one possible solution. There are, again, many factors at work here. Ramesh will now cover a couple more simulations, one of which will demonstrate the sequential valve gating, which is another very powerful solution to the knit problem.
Hey guys, before we go back to Ramesh, and first of all, thank you, Dr. Malloy. That was a really great presentation, and we really appreciate you taking the time to kind of highlight some of the issues associated with injection molding, and then allowing us to kind of piggyback off of that and show some of the capabilities available in SolidWorks Plastics. So thank you guys very much, or thank you very much, Dr. Malloy.
You're welcome.
And thank you guys for staying engaged. Again, keep submitting questions. We're getting a handful of questions. We will answer them at the end of this. And I'm going to go ahead and kick off the second poll. So this, hopefully you guys can see it now. The poll question is basically what if you guys use software now, what type of plastic simulation software are you using? So hopefully that is up on your screen.
All right, so that is really some great information from Dr. Malloy. Some more concepts I want to illustrate, how the injection molding software can actually help, address or be able to predict upfront information. So we're going to take a look at this tensile bar specimen, which is going to be gated on both ends. Now, as Dr. Malloy alluded earlier, one of the things about weld strength is it's very hard to predict, and a lot of material manufacturers may not have the complete data. But I wanted to actually just give you a direction in terms of how you can use the software like SolidWorks Plastics to be able to get a lot of information around weld lines using a simple tensile bar specimen based on the particular material, based on a certain criteria, process conditions that you might be using. So we'll see the effect of how the weld line integrity, in terms of fill speeds, maybe adjusting the melt temperature or the mold wall temperature, how that actually can be valuable information that can be predicted upfront. So this is a simple example, but it's a very powerful way to illustrate or predict, where the weld line forms. In this case, it's going to be dead on the center of this bar. But what we want to do is, like in the earlier examples that I illustrated, we want to actually go ahead and investigate the effect of changing a few parameters. So let's say we start with the default parameters for molding this tensile bar. So we want to fill it in 1.42 seconds. Let's say the melt temperature is 230 degrees Celsius and the mold wall temperature is 50 degrees Celsius. So based on repeating the same workflow process of investigating the through thickness around the weld lines, so in this case we are investigating from the core of the thickness all the way to the skin on the surface where the weld line is, we can see that the default conditions, let's say these are baseline conditions, the average temperature range is about 224 degrees Celsius, and the melt temperature at the gate is about 230 degrees Celsius, resulting in a delta temperature differential of 6 degrees Celsius. So again, the basic guideline of the thumb rule is we want to keep this delta as minimal as possible, so which means that the flow front temperature around the weld line, we want to make sure that it's as close as possible to the melt temperature at the gate. Now, the first variation is, okay, what if I fill it faster, right? So instead of 1.32 seconds, let's try to fill it faster. So with that scenario, everything else remaining the same, just this one variation in the fill time, that actually generates an average temperature across the thickness where the weld line forms. That's about 230.5 degrees Celsius. And so the resulting temperature differential is about 0.5. So that's exactly what we are after. We want that number to be as small as possible. So what if we fill it super slow, like 4 seconds instead of 1.32 seconds? So maybe the idea is we want the melt front to cool off, and we want to see the effect of that on the overall temperature differential. So in this case, when we let it cool off faster, it actually results in a very high temperature differential. In this case, it's about 17 degrees Celsius. So you can see that this can actually affect the overall integrity of the weld. And so a faster fill in this scenario works much, much better compared to a slower fill. So the whole idea is actually you can generate a lot of this type of data. So just a simple tensile bar specimen generate a lot of this data that can serve or become knowledge base or some sort of an intellectual property that your team generates for the entire company for a particular material and for a particular set of process conditions. So to summarize, you can see that based on the criteria that we used, just in this scenario, I showed you faster versus slower fill, and you can see that the faster fill actually results in a nicer, a closer, or the type of result we are after. Now, what else can you do, right? I mean, there's so many other variables you can test to understand how that affects the temperature differential at the weld line formation versus the temperature of the melt at the gate. So that could be tweaking your mold temperatures, tweaking your melt temperatures, and seeing how that actually generates more information for you to make some good or get some good information about the integrity of the weld line. So in conclusion, It can be really difficult to predict directly the strength of the weld lines, but the overall integrity and appearance of the weld lines, cannot be predicted directly. But there are a lot of these leading indicators. I showed you a sample today that can actually tell whether or not we will have a good weld line strength or not. Okay. So bottom line is injection molding simulation software can help with understanding the effects of a lot of physical variables that otherwise it can be time consuming and costly to actually do that on a real physical machine. The next example is again a simple plate with a hole, and we want to understand the effect of having a through hole closer to the gate versus having it as far as away from the gate. So this picture on the lower left side shows you that it's gated on the left side and the through hole is actually on the right side. And the other variation is both the gate and the through hole are actually on the left side. So you want to see how the number one, it actually fills. So that's again a great way to visually understand how right away predict how your cavity is filling. So you can clearly see through these animations how having a through hole on the left versus the right side actually affects your flow front. But what we are after is the weld line. So you can see that when we have the through hole on the left side, we have the weld line that actually can be some sort of a continuous line formation like Dr. Malloy actually talked about earlier. Or you could actually have a weld line like when you have a through hole on the right side, more like a butt weld that can form based on where that hole is located. So what we want to do is take these results and investigate like we have done earlier. Just take a cross section where you have those weld lines and investigate the flow front temperature. So when we have the through hole close to the gate, these are some of the results. The average temperature along that cross section is about 231 degrees Celsius, and the melt temperature at the gate is 230 degrees Celsius, resulting in a delta temperature of 1 degree Celsius. So that's really good. I mean, this weld is going to be really strong, or the integrity of the weld is going to be as expected. Now, when we take a look at the other scenario, where the through hole is away from the gate, we can see that the temperature differential of the melt temperature at the gate versus the where the weld line actually forms, that's about 7 degrees Celsius. So in conclusion, you can gate closer to the through hole, and that can improve the integrity of the weld lines as injection molding simulation software predicts. But it may have a negative effect on the weld line appearance, which may be even pronounced depending upon the colorants or other additives, and it's clearly very well explained by Dr. Malloy and how this can actually affect the weld lines. Now, gating further away from the through hole, we saw that it can actually decrease the overall size of the weld line, but the strength may actually take a hit, may suffer due to the far distance from the gate. Okay, so which can actually eventually cause the weld lines to form at lower pressures and at low and temperatures. So the last example that I want to illustrate today is valve gating. So this part is a simple plate, right? But it's about 3 feet long, 8 inches wide, and about 1/25,000th of an inch thick. Now you can always gate this part using a single gate, right? You can gate it on the far end, and it will fill. But the drawback is you're going to end up with very high injection pressures, which may not be sustainable. So in order to actually go ahead and fill this part in a more amicable way, or be able to reduce your injection pressures, the natural way of looking at it is to add more gates. And so when we do conventional gating, you can see that it gets the job done. The injection pressures can be a lot more lower, but the ramification is that it actually creates a lot of these weld lines, as shown here by these black lines. Okay. So The natural way to actually address this type of issue, or how do we get rid of the weld lines, is we can have the same sort of runner system configuration, but we start valve gating it sequentially, open like an on and off condition of the valve gate. We sequence it automatically, and so you can hear in this example using valve gating, you can see that literally we get rid of all the weld lines that we have seen before with the conventional gating system. So in summary, for large parts like the one illustrated in this example, it is possible to fill the part with one gate, but we know that it's going to result in injection pressure spikes, and you might actually go from have a need to go from a smaller machine to a larger machine. Now, multiple gates obviously help decrease those injection pressure requirements, but obviously result in major weld lines, and so the industry standard solution is to addressing that is valve gating, not only reduce injection pressures, but also to mitigate or eliminate the weld lines altogether. So that is my presentation. I'm going to hand it back to Omar.
Yep, thank you very much, Ramesh. Yeah, great couple demos really highlighting what SolidWorks Plastics can do.
Okay, well, thank you everyone for attending this webinar. We sincerely appreciate your support and your consideration. I'm going to keep this relatively quick because we already have a lot of questions that are already in that we're going to need to answer, and as these guys have already reminded you, please continue to type your questions in now while you're thinking of it, and while we have Bob here to to provide his insight to plastics part design and these weld line issues in general. So just briefly go over the SolidWorks Plastics product portfolio, we have 3 packages: standard, professional, and premium. And basically with the standard package, you can simulate the filling phase of the injection molding process, answer some basic questions. Will your part fill? As we've seen today, will there be weld lines? Will there be air traps? Where might you best gate your part, to achieve the best filling possible. From that, we step up to SolidWorks Plastics Professional. That extends the simulation into the packing phase of the process. That basically then allows you to design and optimize single cavity, multi-cavity, and family mold layouts. Finally, you could step up to SolidWorks Plastics Premium. We add cooling analysis and warpage analysis on top of the fill and pack that you get in standard and professional. That allows you to design and optimize your cooling systems, as well as predict and determine the causes of your molded part warpage, as well as it allows you to investigate various what-if scenarios to solve those types of problems. Some of the highlights from the latest release of SolidWorks Plastics, this is just to kind of give you an idea of what we've been working on. You see the bullet list, the laundry list on the left-hand side of the screen here, geometry-based boundary conditions. So one of the unique advantages of using a package like SolidWorks Plastics, it runs fully embedded inside of your SolidWorks CAD environment. That allows us to do some unique things, which is, you wouldn't be able to do in a standalone simulation application. And one of those unique things is geometry-based boundary conditions. That means your injection locations, your material settings, and various other boundary conditions and constraints can be set relative to your CAD model. So not your simulation mesh model. This just allows you to streamline your workflows and basically be more productive in the same amount of time. In 2019, we also added some enhancements that allow you to design more complex cooling line layouts. So for example, we can now handle conformal cooling line layouts, which is, are becoming more and more commonplace due to the advances in metal 3D printing. And another unique thing that we get from being embedded in the CAD system is we can take the warpage results that I just mentioned that we get out of SolidWorks Plastics Premium, and we can export those. We can export your deformed shape as a SolidWorks part file, which then allows you to read that part file back into SolidWorks and perhaps compare it to the original geometry, or compare it with some mating geometry to see if the warpage that you're getting is acceptable or unacceptable, because just because a part warps doesn't mean that it's unacceptable. This slide just shows some of those geometry-based boundary conditions that can be set, your injection locations, and things of that nature. We started that project in SolidWorks Plastics 2019. We'll complete that project with SolidWorks Plastics 2020. That's the release that's coming out later this fall. This slide just goes into a little bit more detail about exporting that warp geometry as a SolidWorks part. Again, really unique feature of SolidWorks Plastics and really helpful to help you optimize your part designs. Also, in fact, just released with SolidWorks 2019 Service Pack 3 that came out, I think it was within about the last month or so. We released 7 new getting started tutorials for SolidWorks Plastics. These are all, these are basically if you've never even run injection molding simulation software before, these tutorials will help you get up and running very quickly. Most of them run, you can do the and complete entire tutorials in usually less than about 10 minutes or so. So that just gets you into business very quickly with simulation, plastic simulation. Another big project that we've been working on, solver validation and accuracy is always one of our top priorities. So we've partnered with, this is another leading plastics engineering institute located in Taiwan that just happens to be where some of our plastics R&D, plastics development team sits. We've partnered with this, it's called Chengwon Christian University, or CYCU. And run by this guy, Dr. Chen. What we do is we take purpose-built molds that are instrumented with pressure and temperature sensors, and we actually mold a bunch of parts. In fact, in this case, more than 125 unique combinations of part geometry, materials, and injection molding processing conditions. And you can see those are just some of the molds or some of the parts that we made with this study. The first thing we always do is a short shot series correlation. So the top row there is showing these are pictures or photographs of the actual molded parts, and down below you see the simulation. It's the filling front profile simulation or results from SolidWorks Plastics. And basically what you see here is outstanding correlation between the filling profiles that we actually get inside the mold or at the molding machine and those predicted by SolidWorks Plastics. Here's just a second short shot series of another part that we molded in this study. And again, if you compare, how things go across that top row to the simulations that we predict in the bottom row, you can see that we generally nail flow front profiles with SolidWorks Plastics. We dig a little bit deeper. I mentioned earlier that these molds are outfitted with pressure transducers, so we're measuring pressure at kind of different points along the melt flow path. The biggest takeaway from this slide, if you look at the green line, is the experimental value. I always like to say, one of my sayings is we like to know good news soon. We like to know bad news sooner. In this particular case, we found that SolidWorks Plastics 2018 wasn't, the correlation to this pressure curve that we were seeing at the injection molding machine wasn't that good after we got into the packing phase of the process. So we did some work on our solver, and you can see that the results that we get now with SolidWorks Plastics 2019 correlate much more closely to the actual results that we see at the molding machine. We go deeper into the process. Again, these parts that we mold, we measure everything about them. We weigh the parts. We also measure any deformations and resulting part warpage. And again, here you can see probably the biggest takeaway is the lower right-hand corner. The experimental value is plotted on the blue curve. What we were predicting with SolidWorks Plastics 2018 is the orange or reddish curve, if you will, towards the bottom of that graph. And we, again, made some changes to the solver for SolidWorks Plastics 2019. Now you can see that gray line is giving us much better correlation with the experimental results. So the big takeaways of this validation study, these results, by the way, were presented at SolidWorks World earlier this year down in Dallas. We'll actually be publishing these results pretty soon. I think Omar already mentioned that there is a handout that you can download from this GoToWebinar. If you go to the GoToWebinar panel, go to the handout section. It's actually a study that we did with UMASS Lowell a few years ago on SolidWorks plastics validation. But the most recent validation results tell us that our the filling patterns that we predict have outstanding correlation with the empirical evidence that we see at the molding machines. We've already made improvements to the SolidWorks Plastics 2019 solvers to give you better correlation between simulation and real-world results. Part of those solver changes were a new turbulence flow model that we introduced in SolidWorks Plastics 2019 to improve the accuracy of our cooling circuit pressure drop and temperature predictions. And even when we do that, that actually leads to improved warpage analysis results. So, you know, all of this stuff is connected. If we, for example, if we don't get the filling pattern right, it doesn't make sense to go any deeper than that. So we're always, you know, checking the results that we, as much as we can, we're, you know, working on looking at and improving our solver validation and accuracy. I think this is probably the last thing I wanted to remind you about. We have another event coming up in, I think just over a couple of weeks from now, June 21st. It'll be a better injection mold design webinar where we'll teach you about the key factors to keep in mind to avoid some common injection mold design problems. We'll talk about the best practices for optimizing your injection molding designs for the injection molding manufacturing process, and then we'll use injection molding simulation to show you how to predict and avoid some of the most common mold design related defects. And yeah, just to make sure, so that's all the content that I had to present today. I'm now going to turn it back over to Omar, who will manage us through the questions. Omar, I'm sure, which we have quite a few.
Yeah, there are tons of questions coming in. Thank you, guys. I'm not sure that we're going to get to all of them. So the first question that we'll answer is, or that we'll answer that was asked, is going to be go to Bob, and let me just make sure that I have the correct question here. It's